welcome you to the fourth year of this epic seminar series. This is the first seminar of this academic year. And let me open up with an apology for lack of refreshments. Of course, I'm responsible for, I guess, delay in getting the paperwork done for approvals in place. So things fell through the cracks as I was traveling a lot. And so we don't have an refreshment today, but from next time onwards, we will make sure that things are done.
Why don't I work that? Why don't I work that?
I can blame it on work day, I can blame it on the flood, I can blame it on so many things. But ultimately, it's my responsibility. So, today it is my great pleasure to welcome to campus Professor Jeffery Giacomin. He is a very distinguished researcher in the area of rheology, and has had a distinguished career, and you can see the fairly descriptive biography. He has been at the University of Wisconsin for a number of years, before that at Texas A&M, and currently he is holding the prestigious research chairs in Canada, called the Canada Research Chair at Queen's University. That's a way of Canadian government to attract famous Canadians from all over the world back to Canada. I'm sure other countries are also trying this in China and Germany. I've heard they have several programs to get their nationals back to their country by recognizing their contribution in academia and the world. So he holds that prestigious chair, and he is also been the president of the Society of Rheology, and he's currently the editor-in-chief of the Physics of Fluids. Today he's going to talk to us about advances in large-amplitude oscillatory shear fields. You might remember, those of you, some of the older graduate students, about 2 years ago, we had an epic seminar speaker from industry, Prof. Will Hart, and he was talking about the complex rheological problems that they are facing from an industrial point of view when they're trying to fix things, the manifolds and the bone-like structures that they form, and the complicated rheology that they follow up. So this is a counterpart to that in the sense of trying to understand these things from a theoretical point of view, from an academic point of view. And EPIC is about trying to develop an understanding from both perspectives so that we can apply in a very fundamental way what we have learned to tackle situations in industry. So please join me in welcoming Dr. Jeffery.
Thank you, Kumar. I want to thank Professor Nandakumar for inviting me to give the EPIC lecture. This is a great honor. And also for bringing me back to Louisiana. I haven't been to Louisiana in many years. In Canada, we think of Louisiana as a cultural superpower, right? It's a place for good food and art, and there's a reason that there are many good reasons that it's a center for tourism, and it's on everybody's bucket list. And as we flew in, I got to see the Mississippi, the fabled Mississippi River, which was really quite special. We have rivers in Canada, but they don't quite look like the Mississippi, right? It's really wide and mighty. In any event, I went cycling this morning around University Lake, and I saw several things. I'll come to them later in the lecture, but I saw several things that you just don't see in Canada. So anyways, I think this is a very special place. Thank you, Kumar, for bringing me back to Louisiana. Now, this is Queen's University. Now, I think Chris was going to turn the lights down. Chris, are you still there? Yeah, there we go.
Apologies.
No problem. No, now's the time. Very dramatic. There we go. And then this is Queen's University. Now, I see your campus architecture follows a very beautiful pattern. It's got orange ceramic tile on the roofs, and then generally a tan-colored sides to the buildings, and I like campuses that follow beautiful architecture. And by the way, I think that orange tile is like really expensive too, so I'm envious of that. We use slates for the tile in general, Our university is older than Canada, therefore the oldest university in Canada, and we use limestone, which is the local stone upon which the city is built. And so all of our buildings follow this pattern. This is the oldest building on the campus, the theological hall. And for those of us who are old enough to remember the word spell checker, it used to convert the word reological automatically to theological. Right? My lecture today is about reological ideas, and I know you've already heard a lecture from Will Hart at Procter & Gamble, so you've already had some introduction to this subject. But let me just tell you a bit more about Queens. You know, this is North America. There are 5 Great Lakes here. These 2 lakes flow into this lake, right? So that's Superior in Michigan. They flow into this lake. And then this is a bay. This is Huron. This is considered part of Huron. Then that flows into Erie, and then Erie flows over the Niagara Falls into Lake Ontario, and most of our 90 million liters per second is coming from Niagara Falls. You can imagine how mighty that falls is. This lake is 400 kilometers long, right? So if we zoom in on this lake here, and then zoom in a little further, you see Niagara Falls would be around here. And then this is Toronto. This lake is about 400 kilometers long and about 800 feet deep along a ridge that is about 50 kilometers long here in the middle. Kingston is right where it gets shallow. This is where Queens is, right on the waterfront here. It's about 250 feet deep here. And the shallowness causes like islands to be popping up everywhere, and there are about 1,000 islands that then shelter the St. Lawrence River, the mouth of the St. Lawrence River, from the big waves that arise in this lake, and the waves can be 1 meter high. Now I want to talk about shear today. So shear is what happens if you confine a fluid between 2 plates, and then you move one of the plates up and down, then a force will be applied to the opposing plate. And if you divide that by the contact area, you would get the shear stress. But I think you can see that if I apply a large enough displacement to the plates, then these free boundary flows are going to get in the way, and you're not quite going to get the shear stress, which is why you might use a shear stress transducer, and we'll talk about both of that more later. When you move this plate, if you divide its velocity by the gap, then you'll get something called the shear rate. And if you move it back and forth, then you'll subject the liquid to a cosinusoidal shear rate, and that is given by this equation here. Now, the first guy to imagine doing this was Giacomin in 1935, and here's a picture of him in 1935 with his wife just before they came to the United States, where he worked at the University of Wisconsin. So he's the one that conceived the quantity that you might see represented as eta star, called the complex, and called it the complex viscosity. But it wasn't until the 1950s that both components, eta prime and eta double prime, of the complex viscosity could be measured, and that was done done in the chemistry building at the University of Wisconsin by John Ferry and his team. Those of you that have used the WLF equation, this is WLF, Williams, Randall, and Ferry. This is Professor Ferry right here. Well, that test of moving the plate back and forth at small amplitude was really popular with chemists and was used to figure out the connections between molecular structure and rheology, but it became of immense interest to chemical engineers when the Cox Rule was published. And Cox and Mertz were industrialists, and they found that the magnitude of eta star and eta of gamma dot, the steady shear viscosity, were the same thing in the following sense. You see, eta of gamma dot, the steady shear viscosity, that's that thing that goes down with shear rate, right, for complex fluids, for instance, for polymeric liquids. It behaves just like eta star, the magnitude of eta star, when you take omega in the same units, if you will, as gamma dot. So if this is in radians per second, then this would be in reciprocal seconds, for instance. Now, when the experiment is done at small amplitude, this is what I mean. I mean the amplitude of the shear rate is small relative to the frequency of the test. I'm going to divide up my talk with little pictures of Canada, so I'll teach you about Canada here too. Here's a picture of a home that happens to be my home on the waterfront of Lake Ontario that I've been telling you about here. Now, my home, I like to travel, so my home happens to be, the front door happens to be a 9-minute walk from the Air Canada terminal in Kingston, which is convenient. So that's how I started out my trip. Now, the oscillatory shear test is, for chemical engineers, we'll look at it this way, in terms of eta double prime and in terms of eta prime. So, when we perform this test, if the fluid was Newtonian, then a cosinusoidal shear rate would just give us this term here. Eta double prime would be 0, and this would be the Newtonian viscosity. But complex fluids are more interesting than that. You'll get a part that is in phase with the imposed shear rate, meaning in phase with the velocity of the plate. Oops. And then you'll get a part that is out of phase with the velocity of the plate. And we use the symbols eta prime and eta double prime. One is the real part, one is the imaginary part of the complex viscosity. However, if we do the experiment at a larger amplitude, then it's as if the fluid responds in a different language, with a more complicated orthography. And I suppose that language to a Canadian looks a lot like French because it's a Fourier series. You see the grammar here? It's a little odd. What I mean by that, look at n here, you see? So I'm doing the test at a frequency of omega, but the fluid will respond at multiple frequencies. And think of this, every time you have a polymeric liquid in a mechanical device, for instance, say a viscous damper, you're trying to damp a vibration at a frequency of omega, but when you do that, the fluid will generate forces at frequencies of 3 omega, 5 omega, 7 omega, and so on. I think this is one of the coolest things in fluid mechanics, and I've been working on this for nearly 30 years. If I draw an oscillograph here, if I take the left side of that equation and plot it against the shear rate, this is an idea that John Deely had at McGill, then you'll see if that were a linear viscoelastic, if it were small amplitude, this would be an ellipse. But the complexities of the fluid distort it from the elliptical shape and give you a much more interesting shape. Those higher harmonics, 3 omega, 5 omega, are sculpting the shape of the stress response into this interesting shape. And if you try to use, for instance, a cone plate rheometer or any other rotational geometry, traditional one, to make these measurements, the free boundary of the sample here will distort when you try to make large amplitude measurements, and that will prevent you from interpreting the measured torque properly. So if we come back to this local shear stress transducer that John Deely developed, here's one of his latest designs. You will be able to make the large amplitude measurements that you couldn't make on the rotational instruments. And that work was done at McGill University where I did my PhD thesis, and where my daughter graduated just a few weeks ago in chemical engineering. Hey, if we disassemble that shear stress transducer, it looks like this. And then you can mount it into the stationary plate. You see down here the transducer is missing, so you see the hole in the stationary plate. Rheometer has been opened up there, but if you heat it up and then place a sample here on the hot plate, wait for it to melt, and you're ready to close the rheometer, and then move the plates up and down and perform the shear experiment. Okay, that shear fixture is about 75 pounds, takes it about 3 or 4 hours to heat up before you can start doing experiments. This is the way we used to do them, but nowadays there's a series of commercial rheometers available that use sort of the same idea. Instead of measuring the total torque, they put a partition here. See a little gap here. So they just measure the torque in the middle of the sample away from the offending free boundary flows in a rotational geometry. And ladies and gentlemen, this is the future of rheology. For a guy like me, I never thought I'd see the day where these measurements would be this easy to make, and so my new lab at Queen's is equipped with the cold plate partitioning. Let me also point out that we can measure the normal stresses at the same time this way, which we couldn't do with the sliding plate geometry. Here's another picture of Lake Ontario. Lake Ontario happens to be the best sailing in the Canadian part of east of the Great Lakes, and so in '76 the Olympic Harbor was built in Kingston. Well, here's the thing. Imagine life without numbers. I think that's hard to imagine. So let me make the problem easier for you. We're all engineers here. Imagine life without the equations of motion. Now, I actually asked a question like that once, because I remember a guy came to McGill when I was in graduate school. He had just done a sabbatical leave in Italy, and he showed us pictures of the Roman aqueducts, and they were all still working. And I said to him, how did those engineers do that? They didn't even have the equations of motion. And he snapped right back at me and he said, have you ever tried to multiply two Roman numerals? You see, there was a day where our profession existed pretty much without numbers, at least without a proper number system. You see? The equations of motion, of course, would have been of no use at all to those people. Right? We have numbers. We have the equations of motion. But what I've been teaching you about today, I didn't have any equations for. And that went on for 25 years. I got better and better at measuring these higher harmonics, but never really quite knew what they meant. And the main reason I didn't is because I didn't even have a single equation for example, the third harmonic, n equals 3, in the Fourier series that I showed you earlier. And one day I complained about that to Bob Bird at the University of Wisconsin, where I was for 20 years before I went to Queen's. And Bob said, I know how to get an equation for that. And I said, I don't think you do, because I had been trying for 25 years. And he says, I know how to do it. It's going to take some time. It's going to take us the whole summer. And that's the part of the story I want to begin with. Here's Bob in the Perkins restaurant. It's his favorite restaurant. He says it's his favorite because it's the only restaurant in America that has not yuppified their menu. I don't think Bob would appreciate your cultural superpower here. He doesn't even like pepper on his food. I think he would spontaneously combust, right, with most of the dishes served in Louisiana. Okay? But that was a special summer, the summer of 2010. He taught me a lot that summer. First of all, he taught me this is the way you should look at this experiment. I want you to multiply both sides by lambda, the characteristic time for the fluid. Now we see the equation is dimensionless, and when we make it dimensionless, we see the real reason this test is popular is because we have one dimensionless group controlling the amount of nonlinearity in the test, and a separate one controlling the amount of elasticity in the test. This is called the Weisenberg number, and this is called the Deborah number. And everything we say now will be in terms of those two numbers. We can even map them out onto something called a Pipkin map. Nonlinearity on this axis, elasticity on this axis. That's our old friend Newtonian fluid mechanics near the origin there. And the further I get away from the origin, the more important those higher harmonics will be. So he said we should do this with the co-rotational Maxwell model. And I said, I don't really believe you think that's important. And he said, why not? I said, well, I teach from your book, and there's no mention of it in Dynamics of Polymeric Liquids. He says, yes, there is. And he named one of the chapters, and he says it's in one of the footnotes. And I said, well, I don't really think that convinces me that you care about this model. And he says, well, you need to read the first edition. And I said, well, I've never seen the first edition. How different can it be? He says, well, we have two full chapters on the co-rotational models that we left out of the second edition. And then he told me he regretted leaving them out, and this really changed my life as a rheologist. This is where it started. So first of all, he said, it's the simplest relevant model to your problem. You say, what do you mean by that? He says, well, it's the simplest model that actually predicts higher harmonics. The Maxwell model, the convective Maxwell models, for instance, predict 0 for the higher harmonics. So studying those would never deepen my understanding of what I was measuring here. But he said this co-rotational model would predict higher harmonics. Let's learn a little bit more about this before we go into my LAOS discussion here. First of all, what's the idea here? We're going to take the coordinate system and have it co-rotate with the fluid element. We're going to look at everything from that perspective, because a rheologist knows that a solid body motion of a fluid doesn't involve any deformation and therefore isn't important rheologically. It doesn't cause any stresses. This idea goes back to Giacomin in a city in the Czech Republic in around 1911. A remarkably early discovery that he just made by thinking about things. He said, co-rotation shouldn't matter, let's take it out. So now this is a Maxwell model, but no ordinary derivative here. It's a co-rotational derivative. When you do that, you see the viscosity now will depend on the shear rate. See, when the shear rate gets big here, the viscosity goes down. We call that shear thinning. What's more, you will get a first normal stress difference. I think it's amazing that in 1911, Giacomin could see these things would exist, but we weren't able to measure them until decades later. But the first normal stress difference will also descend with the shear rate, and so will the second normal stress difference, and this will even have the right sign. It'll be the negative of the first normal stress coefficient. We didn't actually know that to be correct until the 1960s. So, large amplitude in a dimensionless sense means that the Weisenberg number will be greater than the Deborah number, or that the nonlinearity will be more important than the elasticity. And then here is my co-rotational Maxwell model. I won't go into the details of this derivative here. I wanted to give you the big picture, though, that we're letting the reference frame co-rotate with the fluid element. That's our point of view. And then when you do that, you see why your College of Engineering, wherever you went, required you to study calculus. For me, this was why I studied calculus, or why I was taught calculus. I was just one summer of calculus away from having an equation for the things I had been working on. You see the pattern, right? That it's a series of integrals that we're going to do here. It's a series of integrals, so the answer comes out like that. Look at the answer for the first one. It just has one harmonic, right? So this is the linear part of the response. Pay attention to the colors here. I've color patterned everything. So look at the next one. It's a second order effect. You can see it's nonlinear in the Weisenberg number. See, Weisenberg number really does reflect nonlinearity. That E should be an I. When I was president of the society, I formed a committee. They were supposed to standardize the symbols. That was a good idea, and they standardized the symbols. And they changed the Weisenberg number from WE to WI. If I had to do that over again, I'd have been on that committee. You see? In any event, some of my slides still have E in it. I still can't stop doing that. But you see the blue part there? That's the nonlinear part of eta prime and eta double prime, but what comes along with it, sure enough, and that was a special day for me, the first time I had an equation for the third harmonic. The coefficient, you see out here, that's the amplitude. You see, that's the amplitude of the third harmonic, and it goes with the Weisenberg number squared. And now let's work out that third integral. You see, each time we get an improvement to the first harmonic, and then now an improvement to the previous new harmonic, and now an equation for the fifth harmonic. And that day was a happy day for Bob and I, and the waiter named Paul, a tall guy. We handed him the phone and we said, take a picture of us, and he did, and then he looked at our equation on the screen there and he said, you guys are working way too hard at calculating my tip. You like that joke? Okay, good. Okay, so let's look at some of the predictions. You can see that as we increase the Weisenberg number here, the loops distort more and more, and that's kind of cool. But then since we're doing theory, Bob said next we should calculate the first normal stress difference, even though that couldn't really be measured, at least in 2010, or at least hadn't been published. Now let's look at a paper from 1950 of a remarkable guy named Weisenberg. He just thought this through. No constitutive equations in 1950. He said, well, if I subject it to a sinusoidal deformation, or that corresponds to a cosinusoidal shear rate, then sure enough, I'll expect the shear stress to cause a sinusoidal torque out of phase with the deformation, And then I will also expect a normal stress response about an average value. You see, so there's a zeroth harmonic, and then it will have twice the frequency of the test. And so, indeed, when we do these calculations, we do get results like that. For example, here on the first integral that we do, we get an average value. You see in gold here an average value, and then we also get a second harmonic. But we also, if we do the next integral, we'll get an adjustment to the second harmonic, an adjustment to the average value, and then an equation for the fourth harmonic. And if we continue, we will get the terms, the corresponding terms, including all the way up to an equation for the sixth harmonic. Now the math is getting a little awkward here, but again, for me, I want you to imagine your life without numbers. I spent, my career in a state like that for 25 years. I'm not really worried that these equations are a little complicated. I now have equations for the sorts of things I've been measuring, equations that I can compare with experimental data. In fact, these equations give us loops that look like bow ties. I think you can see why I have an affinity for bow ties. When I would tell students to measure higher harmonics, since we had no equations for them, I would just tell them go by guess and by golly until you can find some conditions that give you higher harmonics. But now, with equations, I can tell them, hey, if you want to make a measurement with the fifth harmonic, you can just follow this formula here, use a ratio of Weisenberg number to Deborah number that is greater than this value, and you should get them. And now I've done an experiment at exactly this value, and you see the fifth harmonic. There's the first harmonic, there's the third harmonic, there's the fifth harmonic, just peeking out of the noise. This rule of thumb actually works pretty well. Now here's another picture of Lake Ontario. We have lots of ducks, and we have lots of loons. And then we also have my daughter, who was in the picture with the loon. Well, we are chemical engineers, and it's nice to have an equation for the sorts of things we've been measuring, but that equation, you notice, came from continuum mechanics, sheds no light on the molecular origins of those higher harmonics. Continuum mechanics is a wonderful subject. It teaches us, when you have a few mathematical assumptions, what the consequences of those assumptions will be. But there's no connection with that in the molecular structure. So my student Schmalzer went over to Bob's office, and Bob began to teach him about the molecular structure, the molecular approach, and then we start all over on the problem with a model called the rigid dumbbell model, which Bob called the simplest relevant molecular model. So now we're looking at the flow a little more deeply, and we want to see how the motions of the molecules might give rise to the higher harmonics in large amplitude oscillatory shear. I want to come back to the Pipkin map here with three colors here. Blue, that's behavior along the y-axis here, that's the steady shear viscosity curve. So when there's no elasticity, when the frequency is low, that's the same as measuring a steady shear viscosity curve. Hey, if I make the Weisenberg number small, and then I'm exploring the behavior along the x-axis, that's the small amplitude oscillatory shear experiment that we talked about earlier. And then I think the most exciting region here is this region here, where we have high elasticity and high nonlinearity. If we think of this in terms of plastics processing, pressure-driven flow through a long tube. That might be the spinneret, for instance, pressure-driven flow through a hole in the spinneret to make fiber, for instance. That would be what goes on along this axis here. On the other hand, we've mentioned the experiment that is used in the chemistry lab for measuring eta prime and eta double prime. That's along here. If you wanted to understand what happens to the fiber after it emerges from the die, when it is shaped into and stretched, for instance, then that might be this part might be more relevant here. Blow molding, film blowing, these kinds of processes are high Weisenberg number, high Deborah number problems. Now, we're chemical engineers, so you know a molecule doesn't look like a dumbbell. So I want you to relax your mind here, okay, because that's a complicated object. That's what a molecule really looks like, the macromolecule really looks like. So I want you to relax away the molecule. You got the idea here? And then now you're thinking, why is he making me do this? Right? Well, throw away the details of the molecule. What is relevant about the macromolecule is that it is longer than it is wide. And if I take one sphere, that is not sufficient, because a sphere is not longer than it is wide. But two spheres held apart rigidly at a fixed distance, we call that a dumbbell. That thing is longer than it is wide. It has length and it has width, and that can teach me about where viscoelasticity comes from and where the higher harmonics come from. Now you say, wait a minute, that thing can't really entangle with other molecules. That's correct. And so when my teeth were cut on this subject, I was taught that entanglements were important, and that was wrong. What's relevant about a macromolecule, it is that it is longer than it is wide, and objects that are longer than they are wide have orientation. And for orientation, we need a spherical coordinate system to describe that orientation. That's right, I plan to explain all of the things I've been measuring in terms of the orientations of the molecules. When I talk about molecular motion, I'm talking about the evolution of their orientations with respect to time. When I take the continuity equation, right, every molecule has exactly one orientation. So the relevant continuity equation here is that. And when I take the continuity equation and make it dimensionless, this relaxant characteristic time jumps out. And it goes with the length of the molecule squared. Think molecular weight here. So the polymer contribution to the stresses will go with a characteristic time that goes with L squared. B is the width of the molecule. That's the diameter of the beads. Now let's look at that continuity equation that I talk about for orientation. You see, here is the time evolution derivative on the left. This thing is called an orientation distribution function, and what we're headed towards are movies of that thing. And it depends on both of the spherical coordinates. So at rest, this is a sphere, right? The orientation distribution is the same in all directions, so we'll normalize that to a constant 1 over 4 pi. And then when the liquid deforms, some interesting stuff will happen. You can't really look into this very easily experimentally. So I think this is an example where theory lets me look deeply into the liquid and get some ideas about how the molecules are creating those higher harmonics. This term here, you notice, does not contain the shear rate. This is the Brownian motion term. This is the term that if I turn off the shear rate, this will make the system spherical again. The orientation distribution function spherical again. And then this is the convection term. This is the term is when I turn on the shear rate, and in my case it's a cosinusoidal shear rate that I'm interested in, that will affect the orientation distribution. These functions are often written down, like look at the gold part and the orange part, they're often written down as functions like this in a compact form, so you may see that lambda of psi and omega of psi, but those things are just these dependencies here. And look, don't worry about the details here, but capital S is sine of theta, capital C is the cos of theta, and so on. These are complicated equations, partial differential equations. They're difficult to solve, and for that, Bob had to teach me spherical harmonics. These equations are just to help me, not you here today. But I do want to give you a sense of the amount of courage I had to develop in order to pursue this, right? Well, as recently as 5 years ago, I would have turned this offer down, okay? But I am not the same guy I was 5 years ago. In fact, this is the future, I think, of my research career. I'm pretty excited about it. So look, the way we solve this is to expand the orientation distribution function in a series of powers of the shear rate. And now you see I have to get each one of these. And to get each one of these, a partial differential equation has to be solved. And when you solve those equations, you will need a new piece of math that I've never seen before, something Bob calls the paren functions. And so when you need to work out those paren functions, Well, what's so difficult about that? Well, the first one is just an integral. It's not difficult. Let's look at the next one, though. Why is that so difficult? It's a nest of integrals. And then the third one, it's a nest of integrals. You say, well, still, that's just a nest of integrals. 1, 2, 3. Why is that so hard? But here's the problem. Look, I've colored some things here. CT double prime, that's a limit to one of the integrals. So in fact, that is why this work takes a long time. These little pieces of math, you know, the first paren function and the second paren function, they needed, now to fit them on a slide here, I'm going to have to take lambda omega squared, you see, and call that capital W, so you sort of get where I'm going here. And then as they increase, they become more and more complicated. But without that math, we can't proceed, and therefore we had to do it. Okay, at the end of the day, we get some beautiful reflections of the moon off of Lake Ontario. These are some nice pictures my wife took. All we've talked about is orientation so far. But all a rheologist has access to is measurement of the stresses, right? We talked about rheometers. So how can I use the orientation distribution functions that I've just calculated to get the things I measure in the lab? You see these angle brackets here? This is called the Giesecke's expression for the stress tensor. And I've written down the part for the shear stress here. It's connected, right? It's connected to the orientation distribution function through these angle brackets. Why? Look at their definition here. See, the angle bracket says anything in angle brackets, take it, multiply it by the orientation distribution function, and then perform this double integral on it. If we do this work in steady simple shear flow, remember shear thinning, for instance? This simple little chemical engineering idea, right? The dumbbell gives us shear thinning. Look at the first term here. It gives us an amount of shear thinning that is not silly either. You can see it's shear thinning because of the minus sign on the first coefficient here. Now you may be worried that a real fluid may not obey that exactly, but remember a real fluid is usually a mixture of different dumbbells, and so as a practical matter we can apply this method for a spectrum of relaxation times, but we won't talk more about that today. We can talk about the first normal stress difference, though, also shear thinning as it should be, and the second normal stress difference in steady shear flow, molecular theory gives you 0. So that's important to remember. This is not quite as good as the continuum approach, but it is connecting us with molecular structure. Now, if we look at the generalized Newtonian model, this is steady simple shear. We will now deepen our understanding of shear thinning by just looking at that orientation distribution function. My x-axis is stretched a little more than the other two axes, so that this is a liquid at rest, but it doesn't quite look spherical, does it? But it helps you see where the axes are to start out with, so it's a little egg shape. I'm going to calculate, I'm going to see what the molecules are up to as I increase the shear rate. Now each one of these points here is at a higher and higher shear rate, you see? And so the red ends, for instance, that's where most of the molecules are. If you want to connect this with your chemical engineering education, I want to integrate around any little circle, for instance, on this surface. The volume between that and the center of the coordinate system is the mole fraction of molecules in that area. Right now I have colors that sort of indicate it pretty nicely anyways, like the red stuff is furthest from the middle, and the molecules are being oriented in that direction. Again, this is steady shear flow. You see the X and the Y. So those are the plates. The plates are moving like this in my experiment at a constant speed. I don't think this happens very much around here, right? But in the fall, things will start to freeze, and that phase change causes a dramatic change at the waterfront in Lake Ontario. I talked to you about the Thousand Islands. Well, these birds colonize on those islands, and they're smart. They're somehow programmed to know that the shore will melt last, will freeze last on our side, you know, on the northern shore of Lake Ontario. So they'll fly all the way over the ice just knowing that there's a few feet of water there that the ducks are not smart enough to stay out of, and they'll rest. That's what he's doing here. He's resting, and then he will get up and take off and grab a duck, right, and bring it back to his family on one of the 1,000 islands. Well, this work we did led to this paper, recent paper, which in turn leads to this answer. Pay attention to the colors here again, right? Blue is for the linear term. And then here's our next expression. Remember now, the lambda here is connected to the molecular structure. So this is my first glimpse at the molecular origins of my higher harmonics. That's this equation right here, and there is the third harmonic. The amount of work here was 10 times the amount of work for the continuum theory. I think you can see why we prefer to solve the problem by neglecting the molecules when we can. Of course, if you're a chemical engineer, you're really hate to abandon the molecules. That's why you went into chemical engineering, right? And if we look at this carefully, we can see the distortions of the stress response from the shapes of an ellipse, which we would obtain for the linear case. I think you've seen that the math comes out in parallel for the molecular theory and the continuum theory. So Bob said, why don't we compare the two? That's the molecular theory for eta prime and eta double prime, and then there's the continuum theory from the co-rotational Maxwell model. And if we put them on one graph, we see a remarkable correspondence, qualitative correspondence between the two approaches. Now that's been known for some time. We'll come back to the comparison, but first of all, I want to focus now on the x-axis here. Let's see what the molecules are doing. Remember, we're explaining all of the behavior here just with the orientations of the molecules with no reference to entanglements, for instance. Now I want to, see that? I mean, I'm rotating, I'm doing an experiment now. You see omega t is going from 0 to 2 pi, but the shape is hardly departing from a liquid at rest. Isn't that interesting? I can explain the eta prime and the eta double prime behaviors with orientation, even though there is hardly any reorientation. These molecules are just jiggling gently about the equilibrium state. Well, now I want to look at that coefficient. We already looked at eta prime and eta double prime. Why don't we look at something at a higher amplitude? And so I'm looking at this first coefficient, first nonlinear coefficient for eta prime and eta double prime. And I'm going to compare that coefficient for the molecular theory and for the continuum theory. And then again, you see what I mean by qualitatively the same. It starts up here, goes down, and then reaches, and then approaches 0, for instance. Same for the continuum theory, and so on. We're surprised to see the two approaches give us qualitatively the same thing. Hey, why don't we look at the coefficients for the third harmonics in the same way, right? With the same sort of graph. And again, we're seeing the same sorts of qualitative similarities. You see, here's the rigid dumbbell dipping below 0 and then coming to approach 0. And here's the rigid the co-rotational model doing the same sort of thing. Well, in the summer, that lake looks like this. But in the winter, that lake looks like this. And it will freeze 3 feet thick. Right? Hey, you can walk on it. Of course you can walk on it. You can drive on it. Right? You can use it as a parking lot, for instance. And so you can strap on some snowshoes and you can head out to any of those islands. That's about a 3-hour jaunt to my nearest island, and it's something I love to do. On the other hand, you're best to bring a compass with you, because if you hit a blizzard, then you're going to need to know which way's home. And if you walk in the wrong direction, that's upstate New York, and you will never make it. That's 50 miles in the wrong direction. Let's look at the normal stresses for the molecular theory. Again, I'm going to need to use the orientation distribution function in exactly the same way that I mentioned before. And then when I do this, I get expressions for the normal stresses this kind of surprised me, but now there's a new set of paren functions that I haven't worked out yet. I said to Bob, how did that happen? Well, here's the cool thing about orientation. Some parts are contributing to the shear stress, some parts are contributing to the normal stresses. You see, some molecular motions are giving rise to the normal stresses that are not contributing to the shear stresses at all, and it turns out you have to do more work on the orientation distribution function than you had to do for the shear stresses here. So away we went and we calculated the normal stress, all of the math necessary for the normal stress differences. Hey, I'm not interested in showing you the details here, but I am interested in showing you how much courage it took Schmalzer to get there for the first normal stress difference. And then there are methods that Bob taught him to make sure that the answer is correct. And the problem here, you may think, oh, that was something that was pumped out by a symbolic math package. It turns out it wasn't. At least we weren't able to figure out how to do that, and we spent quite a bit of time doing that. So we have some help from symbolic math, but most of this had to be done by hand. Okay, enough of that story. In Canada, we also have flowers. I see you have more flowers here than we have there. And in the fall, well, everything turns to different colors. So I think you guys have more color all the time because of your flowers, but there's a particular time of year where colors get really special in Canada, and that's October. Now, here are our answers for the first normal stress difference. I want to go straight to the colors here, but sure enough, our molecular theory is predicting an average value here, and then a second normal stress difference. I really did have my first equation connecting molecular theory with the normal stress response, the second harmonic. We talked about viscous dampers before, but our collaborations with companies that use and design the fluids for viscous dampers, this is companies that make farm machinery, for instance, can now answer questions like, what will happen if I double the molecular weight? Remember the molecular weight, this quantity lambda goes with L squared, so if I double the molecular weight, lambda will increase by a power to the fourth, and then these are forces they'd rather not have, right? Because you're trying to damp a vibration like this. I didn't mention this before, but you're not only getting in-plane forces at 3 and 5, but you're getting normal forces at 2 omega, 4 omega, and of course a steady value also. And so they find these equations useful for redesigning viscous damper fluids. And of course, we've got our old friends, the bow ties, coming out from the molecular theory. And now we can do the comparisons that we talked about. Hey, I don't want to focus too much on this, except to say we found the same remarkable qualitative agreement for the first normal stress difference. Animals choose their colors to match the forest. That guy was right in front of my house one day. Now, I'm a city boy that bought a house on the outskirts of town. So that sort of thing scared the hell out of me when I first moved to Kingston. This is 7 kilometers from my office. But Canada's kind of a remarkable place. I think Louisiana is pretty much the same. You can be right in the city, but you're walking distance from nature, right? I think that's kind of a thing that we have in common here between Canada and Louisiana. You see the deer tracks in the winter, for instance, when you get up in the morning. Let's talk about the second normal stress difference, because this is kind of an exciting difference between continuum theory. You already saw this for steady shear, that it gave 0 for the second normal stress difference. So I said to Bob, I think we're done now, and he says, no, what about the second normal stress difference? Of course, he could see an oscillatory shear, it wouldn't be 0, and so we went ahead and calculated it. We have expressions for what happens to the second normal stress difference too. And they look like bow ties or mustaches, you see, or the other design of mustache. But the bottom line is, for the co-rotational Maxwell model, it's much simpler. The second normal stress difference is just proportional to the negative of the first normal stress difference. And indeed, the qualitative agreements break down here, of course. Now, we've got sort of a driving force for doing some experiments here. We'd like to know if the molecular theory is right or wrong. Is there a difference, or is there a simple proportionality between the first and the second normal stress difference, and that will guide at least part of my research program in the future. Okay, one more movie for you here, but remember I told you the most exciting area would be out here in the large amplitude oscillatory shear deformation, and so let's have a look at this. And now I like this peanut shape because after years of research on this subject, this is at least my first glimpse at what is causing the higher harmonics. Remember, this is the orientation distribution function that we use to calculate that third harmonic in the molecular theory, for instance. And you can see, of course, it's symmetric in time, right? So 0 to pi and pi to 2 pi looks the same. So there's one peanut, and then there's the mirror image of that peanut, boom, right there. Right? These are the molecular motions giving rise to the nonlinear viscoelasticity. Another picture of the lake, and I'm getting closer to the end of the lecture here, but I really had a fascinating summer. I had a student come and visit this summer. She read our papers, and she noticed that when we wrote this paper just about the orientation, by the way, let me tell you about this paper. I told you that some parts of the orientation distribution are contributing to the shear stress. Some parts are contributing to the normal stresses. Some parts to both. Some parts to nothing at all that we can measure with a rheometer. This fascinated me. We've always used rheology to learn about molecular orientation. That's been the main access to what the molecules are doing, this sort of indirect business that I'm showing you here. But it never occurred to us that there were parts of that orientation distribution that were not accessible at all to us rheologically. But when you try to calculate the whole orientation distribution function, then you have to do even more work than I've shown you today, and of course, specifically, you have to calculate that fourth term that I mentioned in the orientation distribution function. And this is Lyell, the student, and she noticed, hey, if you do that, if you already have that, then you could calculate the fifth harmonic too. And so I said, wow, you want to do that? She said, yeah, sure. And so that's what she did last summer. These are the first two terms that I told you about. Remember, this is work. These are results that we got very recently. And now you see the next term in the molecular theory. So now this matches us up nicely with the work we did on continuum mechanics. We now have a molecular theory for the fifth harmonic. And then I don't have time to show you the graphs, but I think you know the outcome here. The outcome is that the coefficients here behave like the coefficients for the continuum model, that their behavior is qualitatively the same. You know, I did my bachelor's and master's degrees at Queen's University, but I didn't remember how powerful this lake was until I came back. I just didn't remember that the wave action there can be as high as the ocean. Here they're about half a meter this day, but last week they were 1 meter high. Now also remember the lake not being so clear as it is today. I think we're doing very good jobs as chemical engineers because you can just see them swimming by. Now 30 years ago that was not the case, but if you're looking for reasons to feel good about the future, right? And look no further than the Great Lakes system, right? It just gets better and better. Of course, there are other ways to feel good about the future. Look into your baby's eyes, for instance, right? I always find looking into a baby's eyes is our first, I call it our first real contact with the future, right? And, that's what we're doing as chemical engineers, building the future, right? Each day we work harder and harder at it. We call it progress. Now some think, okay, that two-sphere model, too simple to be relevant. You really should have distributed the beads along a line. For instance, this looks more like a molecule. But here's the thing. You can do that, and when you simplify the orientation distribution function, the lambda, you see, is still just a constant. It depends on the number of beads you distributed along the shish kebab, okay? But it's still just a constant. So everything I taught you about today is qualitatively the same as you would get for a shish kebab. In fact, if you go from 2 beads to 3, you'll get exactly the same lambda for that equation, you see? And then, of course, the lambda will increase as you distribute them along the chain. But qualitatively, the behavior is the same, which is why lately we've been turning our attention to other models. There's been a lot of work done on molecular theory, but it hasn't been evaluated for large amplitude oscillatory shear, and or what few evaluations have been done have not been compared with each other, and so we've gotten started on this lately. Here, for instance, is a chain model where the angles here can move freely, but the distances between the beads cannot change. And for instance, the Curtis-Bird model looks like that. If you prefer to think of an entanglement theory, then you might think of slip links. And here's another model that has been evaluated in LEOS recently. I already told you about the work that we've done with the rigid dumbbells, but you can also put the rigid dumbbells in a circle to approximate a closed polymer, you see, and some work has also been done that way. If you're working on plastics processing, you know that branching matters, and so some of the simplest relevant models of branching have been evaluated in steady shear. The orientation distribution functions have been evaluated for these, but not for oscillatory shear yet. We're still in a world without the equations that we need for connecting with the basic molecular theories, polymer molecular theories. But that makes the next few decades, I think, exciting in polymer design. Is that we, I think, in my lifetime, we really will reach the point where we can design the molecules from scratch for the kinds of rheological behaviors that I care about in polymer processing. Well, let's talk a little bit about the experiments. I told you about the cone plate partitioning. So here's a new rheometer. It's a commercial rheometer that we got in my lab, and there's the cone plate partition, right, that I talked about. Remember that gap between where the torque will be measured just over this surface, you see, in the rheometer. And now here is, I think I have a movie to play for you here. Let's see how this goes. Sound off. There we go. Okay, so this is a movie that my student Peter Gilbert made, and I'll move it forward. But you can see he's doing an oscillatory shear experiment. In this case, it's a small amplitude oscillatory shear experiment, cone plate geometry. And the boundary is well behaved here, right? That's a measurement of eta prime, eta double prime, and that's what you want the boundary to look like in a logical test. The total torque gives you the same answer as the locally measured torque in the middle of the sample, and you can measure them both simultaneously on the system. But you'll notice every once in a while he steps up in the amplitude, right? As I'm talking here, he increases the amplitude. Chris?
Is it on Giacomin?
What I measured.
What's that?
Was it fine? Do you think they can't hear me?
No, I mean if you want to ready for video.
Oh no, I definitely don't. That was just noise. Yeah, neat idea. That was actually just motor noise in the background, so I don't need that. Thank you, Grace.
No problem.
Oh, look at this though. Now we're up to a higher strain amplitude, and now you see the edge of the sample starts to distort. And I happen to know where the highlights are for this movie. So I'm going to jump. Oh, it's not what I wanted to do. Okay, let me try to do this then. You don't have to start over again. Now I wanted to hit right here. Yeah, there we did jump ahead, you see. Now you start to see the severe distortions that happen at the free boundaries and why you couldn't use the total torque, you know. And then if we jump further ahead, let's see if I can do that here. Jump further ahead. You'll see the liquid starts to crawl away. Some of the liquid starts to crawl away, right, from the surface here. Remember, some of the liquid, you know, if you throw too much out of it, it'll start to affect the part where you're measuring the local torque here. But you can make measurements at larger amplitudes remarkably easily than ever before, right, on this commercial instrument. And don't forget, we have a normal force cell here too, so all of those results for N1 that I talked about can be compared with the measured values. Don't have time to go into it today, but it's well known to rheologists that if you do a pair of measurements, one with a cone and plate, one with a parallel disc, from the two sets of results you can deduce the second normal stress difference, and so we're not too far away from being able to do that too. How am I doing for time? I'm out of time, aren't I? I think I'm 1 minute over, Kumar, right? Okay, nearly finished here. Let me just make a point here, though, that if you make the measurement with the total torque, you can see the red one here, you can see you'll get some effects that aren't actually happening with the local measurement here, which is the whole point of making that cone plate partitioning measurement. And then I think we'll finish on this slide, Kumar.
Beautiful lecture. Very fun. From technical point of view as well as during your final really seasons. We also got to know you as a person. You're beautifully blended. I really appreciate that.
You were too kind.
And I'm going to do flow for questions.
What of the normal pathological behaviors of polymer processing can be attributed to only higher harmonics, like melt fracture, die swell, asymmetric flow, expansions, things like that? Are they all related to inclusions of these higher harmonics?
You know, the outcome, I mean, I wish it had come out that simply, but the outcome is a little more complicated than that. For instance, like when we did the molecular theory, we saw that in order to get the third harmonic, you had to get a correction to the first harmonic. Remember, they came together. So what we learned from that is the third harmonic is actually connected to the first harmonic. You can't separate them. And this is from the molecular theory, not just the continuum theory, but they actually come together. The nonlinearity in eta prime and eta double prime. Now, when eta prime and eta double prime depend on gamma dot naught, that dependence is also connected to the third harmonic. So look, which actual plastics processing problems have we solved with the third harmonic? Well, I actually only know of one that we solved in blow molding, and specifically it was a resin that was being used with the Parasin programming. You know, when you make a bottle and you need lots of melt for the bottom of the bottle, and then not so much for the walls, and then a lot for the part where you screw on. Dow asked us to do a study of a pair of resins, one that was more processable than the other, and we measured the LEOS behavior, and you know, they had obviously studied eta prime and eta double prime, found no difference between the resins, and then for the higher harmonics, we found a big difference for the third harmonic. So I mean, you know, if I were to point you to a paper, it would be that paper. Of course, you know, being able to measure these things well is only now. Only now can I do this in my lab. The old sliding plate approach took a whole master's thesis just to characterize those two blow molding resins, for instance. So I really feel like we're ready to take off now. Was that responsive to your question, Professor Ewing?
That's another one. You said in there that the results we originally dumped out all show that entanglements don't really matter. Now, if that's true, you know, from a real simple standpoint, if that's true, that would mean that if I have two concentrated solutions, one of a beta type solvent and the other one in a jet solvent, that they should almost behave, or they should almost follow the same rheological descriptions.
concentrated solutions behave differently from dilute solutions and from melts and so on. But you notice the sorts of behaviors my lecture has been about. We haven't focused at all on the temperature dependencies of these things. At a given temperature, I think, when we talk about molecular motion being important, we're talking about the orientation. And I have trouble, I've been teaching entanglement for so long, I have trouble stopping. I go right, if entanglement matters, it's only because, I would argue, we're trapping a piece of polymer between two entanglements. So that little network strand, we like to call it, of course, is longer than it is wide, and therefore it has orientation. That's why the shear thinning behavior I'm looking for in a concentrated melt is actually no different from the shear thinning behavior I'm looking for in a dilute solution. And there's been confusion on this, so be careful. When you read papers, even my papers, about these dumbbells, we will call them a dilute suspension. We don't mean that these ideas only apply to a dilute solution. Dilute suspension means we're explaining all the behavior with one dumbbell. So far away from all the other dumbbells, they're not interfering with it. And that idea is sufficient, at least qualitatively, for explaining the sorts of things that I've been measuring for 30 years now. Getting it quantitatively correct is another matter, and we're just embarking on that journey. But that's a more complicated story, getting it quantitatively right, because our fluids are all dispersed. They're all mixtures of chains of different lengths. On the other hand, the cool thing we learned from the molecular theory is, remember, lambda went with BL squared. Right? The first thing you learn in molecular theory here, if you believe it, is it's not really the length of the molecule that matters. It's not really the width of the molecule that matters. What matters is the product of BL squared. So when you have a mixture of molecules, all of the molecules with the same BL squared will be contributing at the same lambda. That's a complicated fact.
Yeah, quick question. That was my other thing too about chain entanglements. That's a different thought or process, and I'm not extremely an expert in rheology. But what about other molecular forces? So you use the term dilute suspension so that you can just isolate the dumbbells from interacting with any other dumbbell. It would be very similar to a dilute solution. But most of the systems that perhaps display the most interesting behavior don't represent that, right? And what do you think it's going to take from a molecular theory standpoint to capture some of those molecular interactions that do play a very strong role in the observed rheological behavior?
Yeah, I mean, that's a good question, but I basically come back to what I said before, that the rheological behaviors, for instance, are not dramatically different between concentrated melts and solutions. So actually, even though let's take the polymer solution, for instance. Since the concentrated solution, since its behavior, when I say qualitatively the same, for instance, the shape of eta prime will be like this. The shape of eta double prime will be like this. That's true for melts, concentrated solutions, and for dilute solutions. So, the interactions that you're talking about, they may exist, but they don't seem to be impacting on the rheology, because I don't think they impact on the orientation distribution function very much. It's certainly not what I was taught 30 years ago. In fact, I was taught that orientation didn't matter unless the flow was extensional, unless you had some strong departure from the equilibrium distribution. We were taught that orientation orientation didn't happen in a shear flow, for instance. I don't know, I think if there are molecules interfering with what's going on here, it's some minor effect. I mean, the main behavior is captured by the rigid dumbbell. Others like the idea of strands stretching, for instance. Again, I was taught that elasticity didn't come from orientation. It came from the molecule stretching, like a rubber band. Well, let me tell you, if I replace a rigid rod with a spring, all the higher harmonics disappear identically, mathematically. It reduces to the convective maximum model, mathematically. So you will see some cool molecular theories that try to fix that problem. They can't fix the problem with a Hookean spring, so they try to hook it up with a more sophisticated spring, some nonlinear spring, and so on. But this troubles me, because in science, we already have a model for two spheres that explains, at least qualitatively, the behaviors quite well. When I put in the simplest spring model, all the behaviors I've been measuring for 30 years disappear identically. So my next logical step would not be, oh, I must need some more sophisticated spring in there. I've already got what I need. You see? And of course, the complexity, when I put the oddball spring in there, I still need to calculate an orientation distribution function. It's just a more complicated thing, because now the molecules are not just reorienting, they're getting longer, right? Or shorter, compressive. So that's called the configuration distribution function, and it's a much more complicated thing. I'm happy to go there if I'm convinced I need it, but I'm not sure if I need anything else here. Ayana.
Thanks, Prof. Jeff. One question I had is about you're making this connection between continuum mechanics and molecular. Is there a way of confirming the dissipation? Let's say you are trying to predict. You always think of viscosity and methodology. Eventually, we dissipate away all this energy of the system. And we're taught that at the molecular level, they should turn into some sort of heat or radiant temperature. So, could you comment on something about various geologies and how temperature should be measured in these molecular systems?
So, Professor, I didn't ask you how to pronounce your name. Is it a soft G or a hard G? Tiagi or Tiagi?
Yeah.
Tiagi. So Professor Tiagi asked a good question, and I sort of ran out of time, so you're going to think this was a planted question, you see? And then I'm back on the lecturing mode here. But Bob and I said, hey, the temperature is rising. Why don't we calculate the temperature rise? Right? So here we are in simple shear. Now, if you walk around the lab, there are all kinds of rheometers with different thermal boundary conditions. But we're just going to focus on the simplest, worst-case arrangement. Let's consider two ceramic plates, and now we'll calculate the temperature rise. I know you think you started me again, but it's just two more slides. I was very close to the end here.
That's rather than a natural course.
Yeah, but here's the thing is, when I started doing these calculations, you see, we normally think of the average temperature rise over one cycle. Hey, think of those viscous dampers, right, for the farm machinery, for instance, right? That fluid heats up. They need to know how hot it gets. But the thing is, right away Bob realized, look, there's not just an average temperature rise, there's an oscillating part to the temperature rise. Why don't we calculate that? And when we did, we found that the oscillating part goes with twice the test frequency, 2 omega, 4 omega, 6 omega, and so on. You see the tildes are to represent the oscillating part here. So here's our equation for the time steady temperature rise. And now here's our equation for the oscillating part of the temperature rise. And then here is the connection between the 2 omega component of the temperature rise and the third harmonic. You see, these things, we used to say, because the average temperature rise, when you do the integral, the cyclic integral, to calculate the temperature rise, all the higher harmonics disappear. Because it turns out the integral the relevant integral over 3 omega and 5 omega and so on, they all go identically to 0. We always thought those higher harmonics didn't matter for temperature rise. But it turns out if you care about the oscillating part, and if you're worried about your polymer degrading, you care about the peak values of the temperature during the operation, then you see the third harmonic, for instance, governs the second harmonic in the temperature rise. And then finally, you know, if you do a real example, for instance, you'll find that the oscillating part of the temperature rise is about the same order of magnitude as the average value of the temperature rise. So if you're worried about keeping it under the degradation point of the polymer, you do need to worry about the oscillating part of the temperature rise. And now, I don't like to give an answer that long without another picture of
Thank you so much. Please join me.